Hello, SICB Plus. I am really excited to share with you my talk on new dimensions in data visualization, viewing fitness landscapes in virtual reality. My name is Acacia Ackles. I'm a PhD candidate at Michigan State University in the Integrative Biology Department, and my research advisor is Dr. Emily Dolson in Computer Science and Engineering. So I like to start out with my acknowledgement slide. Of course, my funding sources, the NSF and Beacon, the Center for the Study of Evolution and Action, as well as MSU's funding itself for my advisor. I also want to acknowledge Austin Ferguson and Kate Scotchless, two of my fellow graduate students who have kept me sane for the last 2 years, and Charles Orfria, one of my mentors at Michigan State University, who provided a lot of helpful guidance on this project. So I'm really interested in studying biological systems, no matter what that system is. So I'm interested in sort of the connectivity and complexity inherent in biological systems. For example, I'm interested in everything from how networks of genes interact with each other and create really complex genetic structures, to how networks of organisms interact with each other and create these complex ecological structures. And as part of that interest, I look at how genotypes create phenotypes, create fitness. So this is known as the Genotype Phenotype Map, and there are a lot of different ways to think about what this means. Two common visualizations. One, if you're sort of more mathematically inclined, is this idea of a large sort of space of different variables, different parameters, different expression levels within genes mapping onto a smaller phenotype space, limb length, jaw strength, all these kinds of biological things we think about, which then maps onto this linear fitness variable where you just assign a single value. A slightly more sort of visually inclined metaphor might be this genotype space where you have all these very particular values that sort of gets projected up into a phenotype space where you have more of abstract concepts of where things might be in phenotype space. And then you have this topological idea of what fitness looks like, where for every space in the genotype or phenotype space, you have a corresponding value of fitness, and it creates this sort of topology of the fitness landscape. And that's what I'm going to focus on talking about here, and how we can better build intuition for what those landscapes look like. So fitness landscapes are a popular biological metaphor. They were introduced generally by Sewall Wright about 100 years ago, and he drew this really nice sort of topographical map where the plus signs here are peaks and the minus signs are valleys, and you imagine it, you would read this just like you would read a map of a hilly domain or something like that. In recent years, we have sort of these more advanced visualizations where you can really imagine the 3D structure of these landscapes by projecting them onto a computer screen or having computers draw these sort of nice shaded perspectives for us. And these are, again, what we call fitness landscapes. The reason that these are interesting and important visual aids for understanding evolution itself is that a lot of the times we're not quite interested in just the shape of the landscape, but we're interested in how organisms traverse the landscape. In particular, we're interested in how organisms get from a place of high fitness but not optimal fitness to a place of optimal fitness, when to get between those two places, you have to go through a much lower fitness valley, as you might say. And this problem of valley crossing has captivated scientists in a lot of ways. And there's a lot of different explanations for how valley crossing could occur. For example, multiple mutations or other kinds of ways of bypassing those valleys entirely. So it's crossing fitness valleys. In particular, fitness landscapes themselves are a very powerful and popular visual metaphor for understanding how you might cross a valley, because you can see the different paths that an organism might take across that valley. However, these landscapes can also be really misleading, especially if we don't have as much information about the landscape as we think we do initially. In order to give you a visual example of this, here's a 2D slice of a 3D object, which is often what we're looking at with fitness landscapes. We're looking at two variables in a very multidimensional phenotypic space. For example, we could focus on just, limb length, like I said before, and jaw strength, but, organisms have metabolic rates and numbers of teeth and just, gestational period, tons and tons and tons of different parameters that form its ultimate fitness, but sometimes we're only interested in two values, or we can only really look at two values. So here's that analogous representation here. This is a two-dimensional slice of a three-dimensional object. And what do you think that object is? Your instinct might be to say that it's a sphere. Maybe you think it's a cylinder. It's actually an elephant. So these, when we talk about reducing dimensions and losing information in that dimensional reduction, it's not just the kinds of information that you can extrapolate from the reduced information, it's the kind of information that might be completely impossible to see without an extra dimension involved. In particular, when we look at this in fitness landscapes specifically, it's called extra-dimensional bypass. Remember, we're interested in how organisms can cross fitness valleys in order to evolve towards higher peaks of fitness in this metaphor. And one way that they can do that is through bypassing that valley entirely in a dimension that we were not aware was there or that we were ignoring initially. So you can see from here, if you took this 2D slice of this landscape, you could go sort of behind that landscape in order to traverse from A to B without crossing a valley. Great, interesting, cool. If we look at 3 dimensions, it's more informative than 2 dimensions. But when you look at this 3-dimensional plot, you might say, okay, but there are still valleys here. How would I get from this point that I'm pointing to with this first arrow to the second point with the green arrow without crossing any of these valleys? If you're looking at this in 3 dimensions, you can't. But there could be a 4th dimension in which it is possible, or a 5th dimension even. This extra dimensional bypass, maybe, if you think about it that way. So in general, expanding our understanding of dimensions and how much we can visualize is going to be helpful in understanding the ways that populations evolve across these fitness landscapes. So in summary, what we want to do is add dimensions to our visual models of fitness landscapes in order to build intuition. Now, of course, we can't just add dimensions on forever. It's not like we can create at this point in time a 600-dimensional visualization, even though 600 dimensions might be exactly how many the phenotype space actually has. But if we add dimensions slowly one at a time, if we can even take it to one more dimension, we're adding in an extra set of variables, an extra whole parameter of information that we can visualize and work with and understand these sort of higher dimensional models and start to build towards an understanding of higher dimensional systems. And the way we do this here is using VR. So VR, virtual reality, are these headsets that allow you to put them on and you experience this depth effect so that it feels like you are standing inside the visualization itself. These are becoming more commercially popular, commercially affordable in the sense of like a gaming console. And there are also a lot of web-enabled tools so that if you don't have access to a virtual reality headset, you can still view a lot of virtual reality-esque things on the web or on a smartphone even. So that's what we've done here is we've taken visualizations and put them into a web-enabled virtual reality database. So to recap what we were doing, how we did this, we built a fitness model landscape, or built a model fitness landscape based off of some parameters, evolved simulated organisms on that landscape, and then visualized the landscape and the phylogeny of the evolved organisms in 3 dimensions. Now, while these first 2 steps are really interesting, and I'm really happy to talk more about them afterwards if you contact me through one of the methods I'll give you at the end of this talk, I'm really going to focus here for the rest of this presentation on this visualization aspect. I just want to give you a taste of what kinds of things we can see in virtual reality and how we are looking to expand that in the future. And if you're interested, hopefully you can give me some ideas about what kinds of things you're interested in seeing as we develop this further. And just so that you remember what you're going to be looking at, you might think, oh, well, this is already a three-dimensional landscape. Am I just going to be walking around in one of these? Well, no. These landscapes that you see on the screen have two variables or parameters as dimensions, and fitness is their third dimension. What we're visualizing is three variables with fitness as a fourth dimension. And that fourth dimension is represented in color for now, although we're exploring a multitude of options. Just as a very quick methods, we used A-Frame, which is a web-enabled VR system, as well as D3, which is a data processing tool for JavaScript. So you should be able now to see my other screen here. I'll try to move, move that out of the way. So what you're looking at here is that three-dimensional landscape. So each circle, each sphere represents a point in fitness space, and the color, sort of warmer colors are high peaks, and cooler, deeper colors are our valleys. And this black line is the phylogeny that you see traversing the landscape. Further away there's a little bit of fog in order to just focus on the visualization right in front of you. And we are working on other methods of visualizing, but this is what it looks like in a web browser. It's not as impressive as it might look in an Oculus, where you can actually walk around and feel that depth, but this gives you a sense of what it looks like to visualize a 3D fitness landscape. You can see peaks and valleys the same way that you could see peaks and valleys in that two-dimensional landscape with fitness as a third dimension. Here, for example, you can see very high, sharp peaks next to very low, sharp valleys. And you can see the phylogeny traversing into that very high, sharp yellow peak down there. Just to give you a sense of what a different landscape looks like, here's a second one. This is a much more rugged landscape, as in the peaks are closer together rather than being smoothly sort of laid out. And you can tell that by how quickly you notice the colors shifting. So again, here's a very rugged landscape. Here's that more smooth landscape where the colors sort of meld together a little bit more easy on the eye. And in both these cases, we've plotted the phylogeny. I've lost it. We plotted the phylogeny onto the landscape itself. One interesting thing about these phylogenies that you can also see is the way that they take these right angles, which gives us sort of an intuitive understanding of the way that they tend to evolve along single parameters in these systems. So again, these are sort of prototypes, but they give you a sense of what it looks like to see inside a three-dimensional landscape. And this three-dimensional landscape, the three variables could be anything that you want. Here, they're just numbers. But if you're looking at biological information, you can look at, parameters related to organism phenotype space. So in summary, as I pull up slideshow view again, visualizing these landscapes in 3D provides, first of all, we saw an intuitive understanding of a landscape's ruggedness, the proximity of peaks and valleys in the landscape. And also, we see that phylogenies along these landscapes tend to evolve along one parameter at a time. And this is the kind of data that we're able to get just by looking visually at these landscapes, not by performing any analyses, but just by being able to see and interact with our data in interesting ways. So I hope that you enjoyed that. If you want to play around more with the demo, if you're lucky enough to have a VR headset, you can see it right from the web at that link there. Also, please feel free to contact me on Twitter at my email. I also have my website up here. If you're interested in these visualizations and want to learn more about them or see what else they can do. So thank you very much. Have a wonderful rest of your day.